So now let's get to why we're here this morning, and that is our keynote speaker. Glenn Vanderburg is the Vice President of Engineering at First.io, really innovative analytics to predict real estate transactions, but also he's a software developer of over 30 years. And he's going to share a bit about real software engineering with us this morning, so please join me in welcoming Glenn to the stage. Hi, Glenn.
Thank you. Good morning. I have a bit of laryngitis, so let's hope I get through this okay. I love being in front of a room full of developers, and this morning I'm going to talk to you for a while about the essence of our field. Round about 1965, while working as the lead programmer for the Apollo program for the on-flight software for Apollo, Margaret Hamilton coined the term software engineering. This is her last year being honored at the International Conference for Software Engineering. She said that she coined the term software engineering to help give the field legitimacy so that it and the people building software would be given due respect. She recalls that initially the term was met with amusement and was treated as a joke, but partly due to her excellent work on the Apollo software, the idea began to be taken seriously. In 1968, in Garmisch, Germany, NATO sponsored the first International Software Engineering Conference, including many of the most important names in the software field. A year later, there was a follow-up conference in Rome. Now, if you go read the proceedings from these conferences, you'll notice something very interesting. In the first one, in Garmisch, there was a lot of debate. And in the second, there was a lot of certainty. In the first, there was debate and uncertainty and what I would call intellectual humility about what they actually knew about software and about engineering and about how those two things should marry up. But a year later, most of that debate was gone. Now, it's not because during the intervening year they had figured everything out. I'm not going to go into the details here. Some people have written reminiscences of that event, and it turns out that politics had gotten involved. And some participants were trying to get NATO to pony up a lot of money to fund academic software engineering research. So they pretended to a certainty that they didn't actually have. There was no follow-up NATO conference after Rome, but nevertheless, this jump-started software engineering as an academic pursuit. Now, at that time, the mainstream of software development really had no long-term vision of itself, where it was going, where it should be going. They were just writing software and figuring things out. But academic software engineering set off in the direction of what they thought engineering should be, software engineering should be. And they recommended things like rigorous requirements discovery and requirements tracking, formal specification of program requirements that would support mathematical proofs of program correctness, graphical modeling, structured and later object-oriented analysis and design, and what we would today consider very heavyweight software processes. But it fell short. Those processes were unreliable and extremely costly. Some large companies, those that could afford it, tried to use those methods. Despite the high cost, that had a high failure rate. An excellent researcher named Alistair Coburn did some great work in the 90s, interviewing participants in some of these projects. And what he found was that even the projects that succeeded using those academic software methods typically succeeded in spite of those processes rather than because of them, because heroic people on the project wrestled them across the finish line and in some cases went around the process to do good work. Mainstream development, meanwhile, carried on mostly ignoring academic software engineering, which I'll sometimes refer to as ASE. And this gave rise to a really strange situation. we had a field where the term engineering was reserved for practices that all the practitioners knew didn't work. And that's weird, because in every other engineering discipline, the term engineering is at least informally reserved for practices that people have a lot of confidence in. In the mid-90s, partly as a reaction to this, the Agile movement sought out more appropriate practices for software development, and this really solidified in 2001 with the publication of the Agile Manifesto. Agile was iterative and experimental, where ASE was analytical, Agile was empirical. All the phases were performed in concert, iteratively. Confidence in program correctness came from feedback and testing rather than modeling and analysis and inspection and verification. Over time, the mainstream of software development has bent towards Agile with increasing success. And ASE is still around, but its influence has waned. Well, today, many in the industry have decided that software engineering is a failed idea. And that includes some people who were extremely influential in the early days of academic software engineering, like Tom DeMarco. These software is not engineering arguments boil down to one of two things. Either software doesn't look like what I think engineering looks like, or software development feels more creative, more like an art or a craft than engineering to me. And to be clear, I think it is an art and a craft, but that doesn't mean it can't also be engineering. I want you to notice that those two ways of putting it are really two different ways of saying things, the same thing. They're both based on an assumption of what engineering is, and often that assumption goes unexamined. And yet we in the field still call ourselves engineers all the time. I noticed yesterday there was a comment from the stage from Jack about you all are the ones that do the engineering that uses our products. So how did we get here? How did we reach this state of cognitive dissonance in our field where we can't even agree on what it is we fundamentally do? And the other question I want to ask is, does it matter what we call ourselves and how we think of ourselves? Unlike Margaret Hamilton, I'm not particularly worried about prestige or legitimacy. But the word engineer carries with it a sense of responsibility, a sense of seriousness that I think we would do well to aspire to and hold ourselves to. And plus, it would be good to get the academic people back on our side again, making serious contributions to what practitioners really need. So anyway, back to the question of how we ended up at that weird state. The best way I know to explain this is to introduce the idea of process control models. This is an idea that comes from chemical engineering. Chemical engineers don't primarily design artifacts. They design processes. And so they have tools for thinking about and talking about different kinds of processes and how those processes are controlled and kept on track. They talk about a spectrum that goes from defined on one end to empirical on the other. And here's a quote I want to read that will kind of explain what this is all about. The defined process control model requires that every piece of work be completely understood. A defined process can be started and allowed to run until completion with the same results every time. So some processes are extremely predictable and reliable and repeatable. The quote goes on. The empirical process control model provides and exercises control through frequent inspection and adaptation for processes that are imperfectly defined and generate unpredictable and unrepeatable outputs. This is from the original book on the Scrum Agile software method by Ken Schwaber and Mike Beadle. So empirical processes require monitoring, feedback, and adjustment, sometimes from human monitors, but often from automation. Now, chemical engineers invented this model to talk about chemical processes, but we can apply it to engineering processes themselves. Almost everyone holds a mistaken stereotype of what engineering is. If you were not trained in one of the traditional engineering disciplines, and maybe even if you were but didn't spend 2 or 3 years practicing it, I would wager that you hold the mistaken stereotype of what engineering is. And that stereotype places engineering here on this process control model spectrum. You can easily see that in this quote from Bruce Eckel in an article where he was arguing against the idea of software as an engineering discipline. He said, programming is not some kind of engineering where all you have to do is put something in one end and turn the crank. This stereotype of engineering is an easy, natural thing to believe. It's comforting to believe. We want to believe it can be this reliable and predictable. It's where the idea of waterfall development came from. Waterfall was in use at least 14 years before Winston Royce wrote a paper about it in 1970. But even though Royce said right there under the diagram that this implementation is risky and invites failure, the idea is so natural and attractive that the US military enshrined it as their standard 15 years later in 1985. So anyway, we have these two views. The academic software engineering folks who are still going down that path say, well, we got to keep trying. Software development should be more like engineering. And a lot of practitioners say, well, no. Software development simply isn't engineering. We should stop trying for that. And I think both views are wrong. Here's the thing. Different engineering disciplines are different. They fall all over the place on the process control model spectrum. And academic software engineering was chasing a stereotype, an idealized version of civil engineering, which is the least like software development of all of those engineering disciplines. The fact that so far software engineering failed doesn't mean it can't work. It means that one model and idea of what it should be didn't work. Here's my view. Software development already is an engineering field. It always has been. It's inherent to what we do. We build useful things for people at scale and search for better ways to do that. That's engineering. What else can it possibly be? The stereotype that we were chasing for so long is a caricature of engineering. No branch of engineering really works that way, and some traditional engineering fields don't look that way at all. So we don't need to become engineers. We need to continue to refine our own engineering discipline, as all engineers in all fields do. So here's where I'm going to go for the next 40 minutes or so. I'm going to talk a little bit about the errors of academic software engineering, then talk about what engineering is, not the stereotype, but what it really is like. I'm going to talk about what software engineering is and should be, I think. And if I have time, I'll finish up with a little bit about what I think is next. The errors of ASE. I'm going to be brief with this and skim over a lot of it. The first thing is that they ignored important dissenting opinions. I'm going to read a section from the Garmisch Software Engineering Conference that was put forth by Alan Perlis, who some of you may recognize his name from the early days of software development, an important figure. And the terminology here is different from what we're used to because we hadn't developed the vocabulary for these things that we have today. But I think you can see in it that he was on the right track. He said, first, a software system can best be designed if the testing is interlaced with the designing instead of being used after the design. So this is not waterfall. He's talking about iterative and incremental test-driven development, not necessarily the way we think of test-driven today, but that's what he's talking about. A simulation which matches the requirements contains the control which organizes the design of the system. This is a little hard to understand, but the third point might make it a little clearer. Through successive repetitions of this process of interlaced testing and design, the model ultimately becomes the software system itself. In effect, the testing and the replacement of simulations with modules that are deeper and more detailed goes on with the simulation model controlling, as it were, the place and order in which these things are done. This is an early view of building a prototype and then refining it incrementally, mocking out dependencies and services that you need so that you can test and design pieces in isolation. Do you see how this is an early picture of the kind of development that Agile led us to? Another error, they began with what's called the rational model and a view of engineering as applied science. The rational model is an idea that was described by Herbert Simon in his 1969 book, The Sciences of the Artificial. And it's really just this idea that you make a plan, and you plan what you're going to do, and you refine that plan, and you verify that plan, and you work that all out, and then you do it. In other words, something like the waterfall model. And in his book, The Design of Design, Fred Brooks, who is best known for the Mythical Man Month, said, "The rational model may seem naive, but it is a very natural model for people to conceive. Yet from early on, there have been cogent critiques of the rational model from the design community." David Parnas, an early figure in the history of software engineering, a very important figure and a very smart man, wrote a paper about the rational model as it applies to software development. And he said, "The picture of the software designer deriving his design in a rational way from a statement of requirements is quite unrealistic. No system has ever been developed in that way, and probably none ever will." But that didn't stop the majority of academic software engineering researchers to strive for that path. Back to Fred Brooks again. He addressed the topic of whether engineering is just applied science. He wrote a reminiscence about his days studying engineering at Harvard, and at that time, the head of the engineering department at Harvard was a Nobel Prize-winning physicist, John Van Vleck. And Brooks wrote, "Van Vleck was very concerned that the practice of engineering be put on a firmer scientific basis. He led a vigorous shift of American engineering education away from design toward applied science. The pendulum swung too far, reaction set in, and the teaching of design has been contentious ever since. We'll see later that engineering is not merely applied science." Academic software engineering devalued the role of code. They didn't see code as a central strength of software development, but instead sought to rely on traditional engineering tools like classical mathematics and design documents. But even in 1968 in Garmisch, people warned against this. Friedrich Bauer said, "What is needed is not classical mathematics, but mathematics. Systems should be built at levels and modules which form a mathematical structure." He was making the point that software is inherently mathematical. Dijkstra said the same thing more concisely, also at that same conference. "Our basic tools are mathematical in nature," saying that we didn't necessarily need to replace that with something that looked more like what traditional engineers used. They also devalued code as a document. As recently as 2007 at UPSLA in Montreal, I heard David Parnas say, in engineering, people design through documentation, which is true, but then he went on to say, code cannot fill that role. But I think in many cases it should. Finally, they disproportionately emphasized correctness over cost. This is the well-known cost of change curve from a book by Barry Beam called Software Engineering Economics in 1981. And it measures the cost of finding and fixing errors in a system as a function of time on the life cycle of the project. And this came from researching real projects that were going on at that time. So ASE folks looked at this and said, well, obviously we need to push all of the changes as early in the project as we can while they're cheap to find and fix. But you can't just snap your fingers and do that. You have to build processes in to inspect and verify and analyze and do all that early in the project, and that pushes the cost up across the board. Well, organizations won't necessarily stand for this, and they can't necessarily support it, even if they wanted to. And so there are pressures that push back on this, and this is like stepping on a tube of toothpaste. It squeezes the schedule out, and the whole thing takes longer. The cure was worse than the disease. Cost is always an object. Ironclad, expensive processes won't be used, and therefore they won't be successful. We need to look instead for low-cost, high-impact processes. And additionally, all the projects he measured to gather that data were waterfall projects, which adds interesting biases into the data that will become clear if you think about it. So, what is engineering anyway? Part of the problem is that it's hard to find a definition or even much discussion about engineering per se, as opposed to individual engineering disciplines. Mechanical engineering professor Billy Vaughn Cohen described it this way. Unlike the extensive analysis of the scientific method, little significant research to date has sought the philosophical foundations of engineering. Library shelves groan under the weight of books by the most scholarly, respected people analyzing the human activity called science. Just, search Amazon for philosophy of science and you'll see what he means. No equivalent body of research treats the engineering method. And he's right. In about 19 years of looking, these are all the books that I've been able to find that are really dealing with engineering as a thing independent of any particular discipline. And if you're interested in that, as was mentioned, they're videoing all these sessions, and you can find those from the video. Engineering is simply not like that caricature. If you think back to that Bruce Eckel quote, let me be clear, there is no kind of engineering where all we have to do is put something in one end and turn the crank. Billy Vaughn Cohen wanted to try to formulate a concise statement of the engineering method as a counterpart to the scientific method. And what he came up with was this: the engineering method is the use of heuristics to cause the best change in a poorly understood or uncertain situation within the available resources. That sounds kind of like what we do every day as software developers. And remember, heuristics by definition are fallible problem-solving strategies. So engineering is always going to involve false starts and trial and error and creativity. It's not just applied science. Which leads us to the next thing. Engineering is a creative pursuit. In his book, Engineering and the Mind's Eye, Eugene Ferguson said, "The conversion of an idea to an artifact which engages both the designer and the maker is a complex and subtle process that will always be far closer to art than to science." And way back in 1923, in an address to the Royal Aeronautical Society, aeronautical engineer J.D. North got upset about something and said, "Airplanes are not designed by science, but by art, in spite of some pretense and humbug to the contrary. There is a big gap between scientific research and the engineering product, which has to be bridged by the art of the engineer." Mechanical engineer Gordon Glegg, when he was writing about mechanical engineering, thought this was so obvious to his readers that he worried that other mechanical engineers might push back on the principles and guidelines he was recommending. So he wrote this: "At first sight, the idea of any rules or principles being superimposed on the creative mind seems more likely to hinder than to help. But this is really quite untrue in practice. Disciplined thinking focuses inspiration rather than blinkers it." Again, he was writing about mechanical engineering. In engineering, math and formal methods are just tools. As a father, I have tried to model myself on the father in Calvin and Hobbes. And one of my favorite cartoons is this one. On a vacation, Calvin says, "How do they know the load limit on bridges, Dad?" And Calvin's dad responds just as I would. He says, "Well, they drive bigger and bigger trucks over the bridge until it breaks. And then they weigh the last truck and rebuild the bridge." And Calvin, of course, takes this as quite sensible, and Mom reacts just the way my wife does. Why is this funny? It's funny because it's absurd, right? How many of you have seen the video of the Boeing engineers testing the wings of a 777 to the breaking point? It's easy to Google for. I recommend that you do Boeing 777 wing test. They put the 777 in a hangar and clamp it down to the floor, and then tie chains to the ends of the wings and hook those to winches on the ceiling and start cranking the wings up. I recommend you watch it for two reasons. One, seeing how far they can flex before they break will give you a lot of confidence when you fly. But second, when they break explosively. It's pretty dramatic. When they break, the engineers get all excited. Now, part of it is because we just like blowing stuff up and breaking stuff. But the real reason is it broke when they predicted it would. The test validated their mathematical model. They thought they knew, but they didn't really know until they tested it. Don't ever let anybody tell you, and people have tried to tell me this, don't ever let anybody tell you that software development isn't engineering because real engineers have math to prove their designs are correct. No, that's not what they use the math for at all. They use it to avoid building costly prototypes and testing them. And even then, they build in safety margin. Another example of destructive testing, when Elon Musk announced SpaceX's plan for their new rocket, he talked about the liquid oxygen tank, and when he was describing this, he showed how they tested it to the breaking point. Engineers do destructive testing all the time. Another example is the Tacoma Narrows Bridge. Tacoma Narrows Bridge was designed by an engineer named Leon Moissef, and he was the primary developer and leading proponent of what was then the premier mathematical model of how suspension bridges work. It was called deflection theory. And he got this contract to build this bridge. It was the first time he was the lead engineer on a major suspension bridge, and he decided to show off what deflection theory could do if you really trusted it. Turns out the mathematical model was fatally flawed because it ignored a force. Now, that's quite reasonable. It's a force that nobody had ever actually been able to measure in a suspension bridge before. It was that wind blowing across a bridge deck that is sufficiently thin relative to its length actually generates lift, like an airfoil or a wing. And that started oscillations in the bridge, and more things happened, and it fell down in a 50-mile-per-hour wind. Engineers adopted formal methods to save money. They always strive for robustness and correctness. There are more reliable ways of achieving that, but they're often expensive. And formal methods really help you save that kind of money. Again, in his book, Engineering in the Mind's Eye, Eugene Ferguson says, structural analyses, indeed any engineering calculations, must be employed with caution and judgment because mathematical models are always less complex than actual structures, processes, or machines. And finally, engineering is really driven by practitioners more than academics. This talk actually had its origins almost 19 years ago when, in June 2000, I discovered this wonderful article by David Billington in Scientific American, The Revolutionary Bridges of Robert Maillart. There I learned that, at least in some cases, even civil engineering doesn't look much like our stereotype of what engineering is. It's actually iterative, experimental, test-driven, and full of trial and error. Sounded a lot like software development, and I found that very intriguing. Maillart was a Swiss engineer working in the early 20th century. He was a contemporary of Leon Moissef, and he was exploring this relatively new material called reinforced concrete. Now, engineers were already using reinforced concrete, but they were using it as kind of a cheaper stone. The design of the bridges hadn't changed. Maillart knew that reinforced concrete had different properties, and he wanted to see what it could do. And he thought he could build bridges that were lighter and less expensive, because in civil engineering, the dominant cost is always materials. But he didn't have the mathematics sophisticated enough to really model this kind of bridge. So he didn't, and other engineers criticized him for it, saying that he was irresponsible. But he intuitively understood statics and the flow of forces in a design like this. He did some informal modeling of these things. He built models at different scales and tested them to destruction and extrapolated from that to the full-scale bridge. And he was quite successful and built many dramatic, beautiful, low-cost bridges like this in Switzerland. Later, the math caught up and proved the thoroughness of these designs. Here's another example. The Gateway Arch in St. Louis, the shape of it is described by this equation. It's actually the shape of a simple common object, a hanging length of chain, but turned upside down. This describes a shape called a catenary. It's not quite a parabola. And in that shape, whether it is hanging or supporting an arch, forces are evenly distributed across the length. Now, this principle of why it was a good shape for an arch was first explained by the Renaissance scientist Robert Hooke in 1671. The actual equation I showed you wasn't discovered until 20 years later by Leibniz, Huygens, and Bernoulli. But engineers had known that it was a good shape for an arch for many years prior to either of those events, and they used it. Third example, the magnificent Cathedral Sagrada Familia in Barcelona started construction in 1882. Projected completion is in 2026. It was all designed, the majority of the design happened before architect Antonin Gaudi's death in 1926. He wanted these unusual shapes for the towers, including the larger central towers that have not yet been completed. And he wanted the columns on the inside to look like a forest. Early arches were based on circles. Then for a long time, later forms were based on parabolas and catenaries. But Gaudí wanted to go beyond that, and he chose to base the Sagrada Familia on hyperbolic geometry, hyperboloids and hyperbolic paraboloids. One consequence of this is that the arches do not need keystones and can instead be skylights. Like Robert Maillart and the early engineers who built catenary arches, Gaudi did not have mathematical tools sophisticated enough to work all of this out precisely. So what did he do? He employed the catenary principle, building intricate hanging string models using bags of lead shot to model the additional forces, the weight of attics, roofs, and towers, that would be supported by the structure. And as with catenary arches and Maillart's bridges, the math eventually caught up. The current architects who are completing the Sagrada Familia have used computer modeling to prove the soundness of Gaudi's designs. So then, if we understand the errors of the stereotype of engineering and some things about what real engineering is actually like, what is software engineering? I mentioned that it's hard to find a good definition or discussion of engineering independent of a particular discipline, and I really haven't found a good one. But the best description of any kind of engineering, best definition of any kind of engineering I've found is this one from the Structural Engineers Association. And as I read this, I want you to see the tensions here. Structural engineering is the science and art of designing and making, with economy and elegance, structures so that they can safely resist the forces to which they may be subjected. So, with that as an example, I'd like to propose this as my candidate for a good definition of software engineering. Software engineering is the science and art of designing and making with economy and elegance systems so that they can readily adapt to the situations to which they may be subjected. It's not perfect, but it's a good place to start, I think. Since we just mentioned economy, I want to talk about the economics of software development. And this all comes from the work of Jack Reeves, who wrote a wonderful article called What is Software Design in the C++ Journal in 1992. Academic software engineering started by looking at, again, their stereotype of engineering that starts with an engineer who produces a design as a document and then hands that to laborers who then go build the structure. And so then they said, by analogy, then, software engineering should start with an engineer who produces a design as a document and hands that design document to laborers, coders in cubicles, who then produce the software based on those specifications. The problem with this is that we never really figured out how to do that second stage well. We never figured out how to build an abstract design document of software that was sufficiently correct and sufficiently complete and precise for programmers to simply implement it according to spec. The programmers always had to fill in gaps in the design or go back and fix problems in the design or return it to the engineers to fix those problems and fill in the gaps, and inevitably ended up doing a lot of the work themselves. And so almost nobody now has much confidence that that could work. So since these programmers have to do a lot of redesign anyway, let's give them the legitimacy and respect that comes with that and make them the engineers and designers. And this document over on the right-hand side, that's not what our customers pay for. They don't care about source code in files. They want running software on systems they can use. Really, Jack Reeves said, that is the design document. Maybe not the only design document, but a very specific, precise, detailed design document, and the act of writing it is the act of designing the software. Remember how I said that academic software engineering devalued code and they went in search of things traditional engineers had, like mathematics and documents and models? Source code is all three in one. Programming languages are formal languages that have a mathematical basis and structure and well-defined behavior. In our code is the model of how a system works in terms of the modules and classes and names and how they relate to each other. And it's a document that specifies how to build the system. And it specifies it so precisely that building it can be essentially free and instantaneous. Compilers and build systems take that design document and build the working software for us. Now, I said I was going to talk about economics. What's the most expensive part of that top row? It's the third step. First for materials and second for labor. But that's the cheapest part of the bottom row. The most expensive part in our world is the design process. As engineers, we would be foolish, we would be irresponsible to ignore that economic fact. We can design by building and testing prototypes of our design, that is, running it through the compiler. Not in the traditional way prototype is used in academic software engineering of a system you're going to throw away. Well, we think this design is pretty good at parts of what we do. Let's build it and see. And we build the system and try it out. Now, in defense of academic software engineering, this upside-down economics was difficult to see in the 1960s. And when Jack Reeves wrote this, building and compiling was very cheap, but testing was still really expensive, and deployment was very risky. But now we can do a lot of our testing quickly and cheaply in automated fashion. And over the past 10 years or so, deploying to production has been completely automated. And you can see that this is taking this crucial advantage we have, code as document and math and model, and pushing it further down the process. We used to have Word documents that described how to deploy our systems to production. Now we have Chef documents and Docker files and EC2 images and things like that to automate that part of it as well. So ask your friendly neighborhood aerospace engineer how much formal mathematical modeling she would do if building and testing a wind tunnel prototype full scale were instantaneous and free. Now the answer is probably not none, right? But it's a lot less than they do. And in fact, as computational modeling and fluid dynamics modeling and things have become more and more sophisticated, the traditional engineering disciplines do a lot more of their work in that same iterative style rather than using the traditional mathematical methods. A little more about code as documents. I mentioned David Parnass before. In some of his work to try to figure out how to specify requirements precisely, he invented a system called tabular mathematical expressions. Now, I'm not going to ask you to try to understand this. I did at one time. But instead, I produced this, to be fair to Parnass, comically simplified example of tabular mathematical expressions that specifies how division works. Now, it's easy enough to understand. Did you see the mistake, though? Too late. This is a document that has essentially the same specification. This is a Ruby mini-test test case. This is another one. This is an RSpec specification. And this is a cucumber test. And this is a fit fixture. And they all describe how math works. And in my opinion, They're all more readable than a tabular mathematical expression, but that's almost beside the point because they're also self-verifying. As programmers, our documents do work for us. They're documents, but they're not mere documents. They actually do work for us. And test cases written in any of these styles, and these are all kind of, well, 3 of them are Ruby-based things because I'm a Ruby guy, and Ruby was where a lot of the experimentation in different ways of specifying automated tests happened. But every programming language has stuff like this. Tests in this style are useful as documents of how the system is supposed to work. We're getting better and better at using them to show design intent. We're not all the way there, but we're getting better at that. And they have the wonderful property that they can be used to validate the systems that they describe. When it was introduced, Agile methods were called anti-engineering because to somebody with that defined process mindset, Agile seemed dangerous. But empirical processes can be just as rigorous and disciplined as defined processes. It's just different. This is a diagram of the original 13 practices of extreme programming, which was kind of the granddaddy of Agile methods. I built this diagram. In the original extreme programming book, Kent Beck has a chapter where he acknowledges and addresses many of the criticisms of extreme programming. And he does it by looking at each of these practices and saying, well, to take an example, continuous integration can't possibly work because X, Y, and Z. And he says, yes, you're exactly right, it has those weaknesses. However, in the context of extreme programming, it is supported by unit testing and refactoring, which help to make up for those deficiencies. And the whole chapter in that book goes like that, and I built this diagram by going through it and drawing an arrow every place he said, this practice supports that practice. Now this looks messy and confusing and chaotic. How can you trust a process like this? But I had a hunch that there was something a little more structured underneath the covers. There was a better way to understand this. And so I worked on it for about a year, and it turns out there are 4 practices you can pull out because they're not really practices so much as standards you hold yourself to, like coding standards and simple design and 40-hour week. So if you pull those out, you can lay out the remaining practices along a scale that corresponds to the size of the decision that those processes are focused on. Pair programming, you're making decisions about statements and methods or functions in a functional language. In unit testing, you're talking about methods or functions and classes and interfaces, modules. The system metaphor, the simplified architecture, is mostly focused on interfaces and classes and how they interact with each other and the design of the system, all the way up to short releases, which are a way of verifying pretty quickly every few weeks that you've built something that your customer actually finds useful. And then, the really interesting thing is, you can replace that with timescales and the same thing works out. Pair programming works on the level of seconds and minutes. Unit testing works on the level of minutes and hours. System metaphor, helps you make decisions. You consult that every few hours as you're designing major parts of your system, all the way up to short releases, which work on the scale of weeks to months. What does this mean? Well, first of all, any decision you make has to go through this gauntlet of feedback loops to be validated in many different ways before it actually ships to production. Agile methods, good Agile methods on a team that is working with them well, they're an economical feedback engine where every decision is validated as rapidly as it is economically feasible to do so for that kind of decision. This is about as empirical process control as you get. And it's a great way of balancing economy and elegance while still caring about robustness. So, Agile isn't the be-all, end-all of software engineering. There's more to it than that. I want to close with a few other things. Academic software engineering was too prescriptive. Everybody was striving for, we're going to figure out the way to do it. But real software engineering must be diverse and contextual. Different circumstances call for different kinds of rigor. Where I work at First, we build a mobile application backed by a web-based service. That service is written in Ruby on Rails. That works great for us. If we were to start it over today, I might choose something else like Elixir and Phoenix or something like that. But Ruby on Rails is great. It helps us move fast. Adherence to Rails' conventions makes the system relatively easy to understand. And good testing coverage gives us confidence that we haven't broken things. But then boundaries between systems are fragile points in large systems. And so the API is GraphQL because it has types and a schema, and it forces us to be very clear about the calls and the data that flows in both directions and about changes we make to it. The mobile app is a whole nother thing. The release schedule is slower, and as the closer you get to the user interface, the harder it is to build automated tests that really give you confidence in the code and also don't slow you down a lot. Partly as a function of that, our mobile app is TypeScript and React Native. The static typing of TypeScript gives us useful compile time guarantees and catches many errors before they ship to production. And React gives us tight controls on how state is changed and makes the system easier to reason about. Distributed systems need support structures. If you're building a distributed system or microservices-based architecture or use a lot of serverless components, you need good monitoring and recovery strategies for those things and alerting. You need distributed logging and tracing so you can make sense of anomalous situations and how your system responds to particular events. Ideally, you need something like visualization of event flows to make the system comprehensible. Not coincidentally, good engineers have built tools for all of these things to help them deal with distributed architectures and be responsible engineers in understanding their system and validating that they work properly. Moving to the cloud has pushed us towards new strategies for deployment and recovery. I've already mentioned fully automated provisioning, configuration, and deployment. And that has led to sometimes, playbooks for certain kinds of runtime events where particular instances of a service are malfunctioning. The standard thing to do is just kill it and let the autoscaler restart it. And in an environment like that, that's not a crazy thing to do. It's a perfectly reasonable approach when you've done the engineering right. That leads to chaos engineering, which is simply an acknowledgement that failure is going to happen, and the best thing to do is to get good at dealing with it. This is something that the telecom people and Erlang people have known for a long time. When we all had our own data centers and maintained all of our own servers, we could convince ourselves sometimes that, well, we can just do it and be careful and make sure it doesn't go down. But when you hand that job over to a cloud vendor, you can't convince yourself of that. It was never true anyway, but you can't convince yourself of that anymore, and the cloud vendors are explicit about it. They have, certain levels of reliability they guarantee, but it's not 100%. And so Netflix responded to this by building Chaos Monkey, which would randomly kill services in production and force themselves to build systems that could deal with that. Again, to somebody with a defined process mindset, that seems nuts. but it's very responsible software engineering, and it started with that server failure thing and now has grown into an entire sub-discipline with many tools that simulate or actually cause many kinds of failure and anomaly situations to prompt teams to get good at dealing with those systems and build architectures that can be responsive to them. You'll notice a lot of the things I've been talking about in the past few slides are things that happen after your system is in production. There's no one place to go to gain expertise on all of those kinds of things, but the best one-stop introduction to it, I have to plug my friend Mike Nygaard's book, Release It, which is a fantastic book about how to build systems that behave well after they ship. And that's part of software engineering too. Software engineering, as I've described it, applies to machine learning. In machine learning, what you get out of a model is a function of what you put into it. And there are all kinds of examples of this. My favorite, remember when iOS 11.1 would autocorrect a standalone I to A and an unprintable Unicode symbol? You must take care to understand the quality of your data and account for that in your models. And that includes all the data that's used in every part of machine learning. Yesterday we saw some great examples of how Esri's products make it easy to bring their data into machine learning models and build those to learn very interesting things. But the fact that you can enlist the computer in figuring out what the program should do doesn't absolve us from the responsibility as engineers to make sure it does reasonable things that is what our customers and users expect and want. And so you have to take all of this into account. And not only all the data that goes into the model, but the assumptions that go into it. And you have to guard against not only outright errors, but subtle biases. I'm continually impressed with how hard our data science team at FIRST works on this. I've learned a lot from them. And finally, as engineers, we need to care about ethics. Traditional engineers are trained in engineering ethics, and software engineering programs are starting to do the same. I'm delighted that my son, who's a senior in computer science at Texas A&M University, is required to take an engineering ethics class as a part of his degree plan, and he's taking it right now. It wasn't that way when I took computer science. Software systems can powerfully affect real people. Many systems built on Esri's products are systems of record. And by having incorrect rules or too weak security or sometimes even too tight security and authorization rules, or by sometimes getting the data wrong, that can affect real people in harmful ways or advantage some at the expense of others. Increasingly, software systems are the mechanisms of enforcement for laws. And there have already been cases where programmers coded into those systems that help enforcement officers enforce those laws stricter rules than what the legislators actually intended. There are biases that can deny services to deserving people. Ethics are very important, and they're an important part of a software engineer's role. The Association for Computing Machinery and the IEEE Computer Society have produced the Software Engineering Code of Ethics and Professional Practice, and it's actually quite good. I encourage you to seek it out and read it, and you can find it at these two URLs. We are software developers. We are engineers. Let's live up to that responsibility and keep getting better at what we do. Thank you.